You can hear the slide, see the slides, I guess, right?
Yes, we can see.
Right. Okay. So welcome, everyone. So I'll try to highlight some of the findings, interesting at least to me, findings from NICER based for the thermonuclear X-ray bursts, which we have been working on with students here, Ersin Göğüş and many others, especially as well as, of course, the NICER burst and accretion physics working group like Rob and many other colleagues. So my take on from the point of view of burst will be a little different than what Grav just mentioned. I will start from the past a little bit and then continue with the NICER. So there has been already many very good introductions to the low mass X-ray binaries, what the low mass X-ray binaries are and stuff. So I'll quickly skip over these slides, but I just want to mention that in the case of a low mass X-ray binary, we have a small low mass companion star that fills its Roche lobe at least from time to time, let's say, and starts accreting matter onto the compact object. The key point in our case is that the magnetic field strength of the compact object, for example, the neutron star, is not so strong, so that the matter accreting from the companion can actually be basically in time accumulate on the surface of the neutron star itself, so that there will be some accumulation and then there will be some thermonuclear runaway reactions. This is just a typical picture of the famous 4U 1820-30, one of the ultra compact binaries with an orbital period of about I guess 11 minutes. So let me skip to the burst part. And what happens is that when you accumulate matter onto the surface of the neutron star and continue doing that, due to the very strong gravitational field, of course, of the neutron star, within a very short amount of time, the density of the matter and the temperature of it will increase significantly, increase to a value where you can actually start seeing hydrogen fusion into helium, or even in some cases helium fusion to even heavier elements. Even in more rare cases like the superbursts, where you see carbon fusion as well. What we observe, or what we have been observing, let's say, when it comes to the X-ray bursts, looks just like this. These are on the x-axis we have the time relative to the burst start, and on the x-axis this is the RXT data, by the way. Basically, the number of counts that we observe from these objects. So these bursts typically last about tens of seconds, at least the shorter ones. And they show a very much similar profile in intensity with a fast rise and a roughly exponential decay. So with the RXT, which was launched in 1996, we were able to actually, for pretty much the first time, let's say, extract X-ray spectra of the photons that are coming from a very tiny amount of time within these bursts, and actually see or actually watch, let's say, how the spectral evolution happens through the burst. And from there, we had the idea that these are all thermal events, so that the whole scenario of the nuclear fusion and cooling of the neutron star itself and so on has been actually presented. And if you do that, if you do extract X-ray spectra and move on over the time for example, using quarters of seconds of time intervals, for example, then you can actually see how the spectral evolution happens within the X-ray bursts. There seems to be two types of X-ray bursts. One type on the left-hand side that you see. The difference here is that in each case, the flux increases to some value exponentially, within a very quick amount of time, and then the decay is mostly exponential. Within the RXT passband, which was in the hard X-ray bands from 2.5 roughly to 25 keV, what we were observing is that at the very beginning of the burst, the temperature would increase to some value, which would be typically about 2.5, 2 keV values, and then start essentially cooling, showing a cooling throughout to the end of the burst. This is one of those typical events. But in some rarer cases, we would see that the emitting area that is covered, that is actually represented here in these panels at the very low panel, actually, that you see is that the burst first covers the whole surface of the neutron star, seems to be covering, let's say, but then it doesn't stop there and continues to actually expand. The photosphere expands, as Gürel just also mentioned. And then at that time, we see a relative cooling, decrease in the temperature, which would then, as the photosphere again shrinks back to the original value, continues to increase. These are called the photospheric radius expansion events, bursts that show somewhat different behavior, and bursts within which the photosphere seems to be expanding. These are just a little bit more clearer pictures of the same scenarios, actually, where on the left-hand panel you get to be able to see this photospheric radius expansion events in a much more clearer picture, and in the middle is a typical X-ray burst where we see that the temperature shows a very sharp increase at the very first beginning of the burst, and then at the same time you see an increase in the normalization, which then stops, and then as the burst decays, the cooling, we observe a significant cooling in the temperature, while the normalization of basically the emitting area of that black body seems to be more or less constant. So this is just another way of seeing this. On the x-axis, we have the temperature increasing to the left, and on the y-axis, we have the flux. This very first point, shown in the red, is the first point that we were able to capture, actually. And then all of a sudden, as you can see, we see a very significant increase in the flux. And because this particular example is a photospheric radius expansion event, we see a change in the emitting radius, also in the temperature, because it cools down the expanded gas, and then basically returning back to the original value. The black line shown here is basically a T⁻⁴ line, so it's basically showing how well the apparent emitting area of the neutron star is actually can be constrained. And using these observational properties, it was possible to actually pinpoint several important aspects, physical properties of the neutron stars. First of all, as I mentioned, from the cooling tails of the bursts, one can actually try to infer the emitting area of the neutron star using black body functions and then converting them using some color correction factors and stuff. But making the assumption that the whole surface of the neutron star is cooling as the burst decays, one can actually try to understand the emitting area, total emitting area of the neutron star. One more thing, which is shown to the left, is that in some cases, when the photospheric radius expansion happens, what happens is that, of course, the radiation pressure seems to be exceeding or reaching to the gravitational force of the neutron star, and that's why we seem to be seeing these photospheric radius expansion. And in some of these bursts, one can actually assume that they actually reach to the theoretical Eddington limit for the neutron stars, which again depends on the compactness of the object, meaning the mass and the radius of the neutron star. So if you get to be able to measure the flux at the correct moment, which back then in the RXT era was named to be the touchdown moment, which is basically the moment when the normalization seems to be returning back to the cooling point, and then you assume that this is this actually value, the touchdown, the flux that you measure at the touchdown moment is equals to the Eddington limit, and then from there on you can move on to trying to find the mass and the radius of the neutron star one more time. And we actually tried to do that for a number of sources using the wealth of RXT data and came up with several contours as shown in here for different sources back in 2016. That was the final, those were the final results for several low mass X-ray binaries. But within all these measurements, there were three questions that seemed to be, at least to me, remaining, which were basically, really, do the time resolved X-ray spectra of bursts really follow the Planckian distribution or not, which will be my main topic, which will be the thing that I think will be finally resolved, at least to some degree, with the NICER. And then, do they really follow the cooling tails of the X-ray burst? Do they really show the full surface of the neutron star cooling or just a part of it maybe? And then also, how well the Eddington limits are determined. It's obvious that we make some assumptions, of course, from the touchdown fluxes and several measurement limitations, but even within those measurement limits, is it really good enough or not? So, of course, RXT still has one of the greatest data archives when it comes to X-ray burst observations. As much as I could find, till 2008, RXT observed about like 63 low mass X-ray binaries for like roughly 40 million seconds. Within the MinBar catalog, which was now published a few months ago, I guess, we now know that RXT in total had about like 46 million seconds of observations of these objects. And from 45 of these sources, MinBar catalog now has more than 2,000 X-ray bursts recorded. This shows a huge archive. And back in the time when we were working on it, it was about like 1,000 X-ray bursts and so on. Now, just a plot to show you, and I will show this another version of it actually in a few seconds. But just a reminder that when we did fit the X-ray spectra within the 3 to 25 kV band, these were the chi-square distributions using thousands of X-ray spectra, by the way, including the tails of the X-ray bursts from various different sources. And as you can see, we have found that in a great sample of all the X-ray spectra of all the X-ray bursters, we found that it was actually, let's say, a perfect fit to some degree. And to what degree is actually already hidden in the data, which we found to be about like 3 to 5% levels and so on. Just to again show, this was how the cooling tails were based on the same color to flux, temperature to flux plots. And this was how the normalization values were actually shown to be following as they basically as the flux decays down to about like basically about 1% of the peak flux of the X-ray bursts. We tried to understand whether if they actually really follow the T to the -4 law, or if it's not the case, then how well actually, or to what degree they were showing scatters. And this was just another example for 4U1728. And basically on the x-axis we have the flux decreasing towards to the left, and the normalization value, which is related to the emitting area of the black body on the y-axis. We even saw color correction evolution of the color correction factor. The color correction factor is something that is related. So I don't want to go into too much detail, but even if we use and still do use, actually, let's say, black body functions to model the X-ray spectra of bursts, we do think that the neutron stars have some atmospheres, especially in the case of the matter being accreted onto the surface of the neutron star. And there are some theoretical models that can actually be used to infer physical effective temperature of the neutron stars at these levels. But it's very hard, especially when it comes to such high temperatures, because then when you try to solve the radiative transfer equation, you have to take into account the Compton scattering within the atmosphere, which means that you do not only solve the radiative transfer equation as you move towards higher and higher layers in the atmosphere, you do not really just follow the photon scattering, which will be averaged out when you actually phase, but also you have to follow the energy change in each scattering in the photon, which is actually harder. So when people actually really calculated these atmosphere models, instead of fitting those models directly to the observations, they tend to fit those models with a combination of black bodies and try to find what is the temperature relation in between the atmosphere's effective temperatures and the black body temperature that you would infer by fitting it with the theoretical spectra, and then find something we call the color correction factors. These color correction factors, which is shown, for example, in the y-axis of these two plots, are changing as a function of, first of all, temperature or the luminosity of the burst. And furthermore, they actually do change depending on the assumption of the abundance of the atmospheric layer on the log G, the surface gravity of the neutron star, and so on. But looking from a pure observational point, what you would see, what you would expect to see actually, is that essentially at very high luminosity levels, you would be seeing a change in the normalization factor, because, let me show it here. Because in this equation here, this is the black body normalization that is shown with the A, and this is the color correction factor. If the neutron star radius and the distance actually is the same within the given burst, which you would expect, then you would see, simply by changing the color correction factor, you would see a change in the black body normalization already without doing anything else, let's say. And this is what we would be seeing by within these at the very high burst observations at the very high Eddington limit values. And you would see arbitrary, basically, normalization changes which correspond to the change in the color correction factor based on the theoretical atmospheric calculations. We also worked on, as I mentioned, on the stability of the Eddington limit measurements, the touchdown flux measurements. These are just a few examples. So how do you do those measurements? You basically have to have black body temperature and the normalization, and of course, which correspond to the total flux of that black body. And these contours here show the inferred data parameters, 1 and 2 sigma values for each burst. And then the red dashed lines here show the constant flux regimes. There were interesting sources as well, like Aquila X1, which I will come towards the end of my talk as well, and which seemed to be showing some sort of a scatter in the touchdown fluxes in the Eddington limits. Even such a change in the Eddington limit may be expected due to the fact that, again, coming back to this equation here, now to the upper left, here you have this kappa for electron scattering opacity, which depends on the amount of basically hydrogen abundance in the accreted matter. So if that changes, the touchdown flux or the Eddington limit for a given source will actually change from time. It can actually change from time to time. But pure RXT observations all showed that, apart from some exceptions, these in each case these observations seems to be good within, let's say, 10% or actually a few percent. And then jumping back to the future, let's say to about like 2017, we now have the NICER. Gaurav already gave a very nice and actually a more detailed than me introduction on the NICER and how it actually allowed us to. I saw. There is my slides. Wait a second. Sorry. Very nice introduction to the NICER mission. But I just want to show this video because it really gives an idea on how actually nice is the NICER. Because if you are working on X-ray with the X-ray data, X-ray observations, you're not really allowed to see your own instrument working, apart from NICER, I guess, because you launch Chandra, XMM, whatever, into very eccentric orbits, and then actually practically never see that again. And it just sends you the data in time. NICER is not like that. It is mounted on the International Space Station. And so we get to be able to see it in almost real time. And furthermore, actually, what is probably even more has been proven to be a very good property is that the communication with these satellites can only be done, let's say, when they are passing over a radio dish on the ground. Whereas in the International Space Station, the communication is much more frequent because there are humans there, meaning that we can actually talk to our instrument practically almost all the time, which is great because X-ray sky is actually very much full of transient sources, significantly changing in time objects. So it gives us a chance to actually really quickly direct NICER into different positions in the sky, for example. This is a very nice picture. It's an non-imaging instrument already mentioned by Gural, but using exposure times, Jack Steiner actually did this nice image of NICER, I guess a year ago or something. So this must be even better now. This practically shows all the observations made with the NICER over the span of the time since its launch. The most important property of NICER, as I mentioned, to me is how agile it is, how flexible it is when it comes to communicating with the ground, so that we can direct the telescope to some detectors, to some location in the sky, and so on. But furthermore, what is more important to me is that it has the largest effective area in the soft X-ray band, which was necessary to understand when it comes to for example, burst observations, to understand how well do we make, how good we are making when we actually model the X-ray burst spectra using pure black bodies. Because I probably forgot to mention, but when it comes to time result spectroscopy of the X-ray bursts, we do actually model individual spectra using blackbody functions, but then assume that that's the model valid within the whole electromagnetic spectrum and of the neutron star, and basically convert it to bolometric luminosity to come up with for example, the Eddington limit or the emitting area and so on, which may or may not be correct. And NICER is the tool to actually test that assumption in a very good way, actually, given its very large effective area. This was not possible when, unfortunately, RxD was still functioning in orbit below, actually back in 2012, for example, because XMM Newton or Chandra proved much lower effective areas and actually, in some cases, lower temporal resolution. To date, as much as I could collect, NICER observed since the summer of 2017, NICER observed roughly about 53 X-ray sources, which has been reported to show bursts back in the past before NICER. As much as I know, we have about 245 bursts from 19 different sources, all recorded. And we actually collect all the data of all these X-ray bursters here in Istanbul and actually do a periodic search for the bursts, trying to detect them. And from 19 different sources, I must note that about half of the bursts within this sample is coming from the rapid burster, which shows, in addition to normal thermonuclear X-ray bursts that we have been talking about with Gural, in addition to that, there's some different types of bursts, which is observed only from a few sources, but can be observed much frequently. So, although we seem to have about 245 X-ray bursts, not all of them are thermonuclear X-ray bursts, I should know. Still, we have a good sample, and we already obtained some interesting results. So I will try to summarize them today very briefly. So first of all, we have been able to discover X-ray bursts from SWIFT-J 1858, MAXI 1807, 1621, and so on, and contributed to the burst observations, for example, in the case of 1621. This is all because of thanks to the fact that we can actually, as I mentioned, once the trigger happens from MAXI, from SwiftBat, whatever, we can quickly trigger observations and direct the NICER to these newly discovered sources in this case, or a source that is being reported to be in an outburst very quickly, and start observing them in a periodic manner, actually. And then one other interesting thing which Grau also mentioned, that we have started seeing X-ray bursts with secondary peaks. This is not the first time that we are seeing secondary peaks from X-ray bursts. People has been observing such peaks before as well. But it seems like this is going to be an important topic when it comes to burst observations with NICER as well. Grau already mentioned one such case. I will a little bit go into a little bit more detail on the continued observations of the same source in a different outburst, during a different outburst. And I will show one such example from Aquila X1, which we have just actually discovered practically a few weeks ago. This is the same picture that, this is the same figure that Grau showed. This is the first reported burst with secondary peaks from 1608 within the NICER sample. This has been a very interesting burst, actually, as the picture suggests. But there's one important thing that I would like to note here. For example, when you look in the spectral evolution of the parameters, the blackbody temperature and the blackbody emitting radius, one thing that will be different from the rest of the secondary peaks, let's say, that I will be mentioning, is that these kinds of evolutions, like where you would see increase in the normalization and then another decrease, and seemingly another small increase, and then a more or less roughly, let's say, constant evolution in the blackbody normalization, is something we have been seeing in the RXT era as well. So actually, this is when you look to the left-hand panel, you see a very strong secondary peak, which is interesting. But then, even more maybe interestingly, you do not see such spectral evolution that is, unlike from normal bursts where we do not see secondary peaks and so on. So that's one thing to note, and maybe even compare with the other peaks that we observe. So these are this source showed an outburst in the summer of 2020. So just a few months ago, let's say. We're already in almost end of March, right? So practically last year. So these are the X-ray bursts that we were able to recover or detect with the NICER when the source was at the peak of an outburst, actually, when the accretion rate is much much larger. These are the starts of the burst. These are much later compared to what, for example, Grau found in this case, where the secondary peak seems to be happening at around like 9-10 seconds after the start of the burst. Whereas in our case, basically the start of the burst, the secondary peak happens about like 30 seconds, or even in the other burst case, about like 18 seconds after the start of the initial burst. Now, even more interestingly, in the case of the 2020 bursts, let's say, we see a complete, basically cooling of the initial peak, and then another secondary, basically mini burst, let's say, maybe even a secondary peak where we detect the temperature variation in the temperature and the flux, somewhat more or less the change in the apparent emitting area and so on. In fact, if you actually model the temperature evolution with a exponential function, these are the residuals that you would get to basically show the temperature change in the temperature a little more significantly show. So one thing that we came up with maybe is about the spreading of the spreading of the burst stalls at some point through the equator. So in these cases, as I mentioned, the burst will ignite at some point on the surface of the neutron star. And we used to think that because these are all actually very rapidly rotating neutron stars, in the case of 1608, for example, the spin frequency is thought to be about like 600 hertz, 620 hertz. The burst flame basically covers the full surface of the neutron star within a few seconds, and then the whole emission continues. That's what I've been actually, mentioning to you when the cooling tail happens and so on. But we thought in these cases, in these secondary bursts with secondary peaks, maybe that's not the case. But for that, what we observe is pretty much late, because as you can see, the burst flux practically decays back to the persistent emission level of the neutron star, of the low mass X-ray binary, before actually, and then all of a sudden the secondary peak seems to be happening. So it may be that some sort of a residual accreted material that just didn't burn in the first place started to basically fuse into nuclear reactions and so on. What is more important, and as Gaurav mentioned, as I guess will be very much important in the coming years as well, is the contribution from NICER will be on the observations of soft excesses from the burst, I guess. As I mentioned, back in the RXT era, for example, we used to fit the X-ray spectra using blackbody functions within the 2.5 to 25 keV, and after subtracting the persistent emission from the low mass X-ray binary itself, or in some cases, as I will mention, model them, that blackbody function would perfectly fit the spectrum, and we allowed us to get into the physical properties. But that's not the case when it comes to the, apparently, at least in some cases, they say, that doesn't seem to be the case when it comes to the NICER observations in soft X-ray band. The story started with Aquila X1, already was published in 2018, already starting with practically the first observations. And then for you 1820 minus 30 came, and then 1608, Sachs J 1748, Swift J 1858, Maxi J 1807, and several others that are not published, but we have the data and so on, and see that. This is a figure that Gaurav already also showed, which shows on the x-axis the energy, and on the y-axis, on the upper panel, we have the counts per second per keV, and the lower panels show the residuals from a pure blackbody emission. As I mentioned, during an X-ray burst, you do not just see the whole X-ray burst, but also continue to see the X-ray emission coming from the accretion disk itself. This means that you have to take the pre-burst or post-burst, or whatever you would like, actually, as kind of a background to be able to, which will be subtracted from the burst emission, so that you can come up with the pure, let's say, blackbody function or burst emission, or at least take that persistent emission model into account, because that's still, I mean, even though bursts are very much bright, the persistent emissions still contributes, especially towards the cooling, to the decay or to the end of the burst. So basically, what is shown by Lawrence Key here in with the blue dashed curves is basically the pre-burst emission compared to the burst data, which is shown in the sound burst plus persistent emission data. The red curve here shows the best fit Plancking function, and you get to be able to see already these significant and systematic residuals at the soft X-ray band, which you can eliminate by simply multiplying the pre-burst emission with a factor which we call the FA factor, or actually even taking into account a little more physically motivated model and actually do the disk reflection calculation. This is again still the same figure that Gaurav mentioned on the 1820, and you get to be able to see that at the peak of the burst, the persistent emission needs to be multiplied by a factor of 3. It shows that the persistent emission actually somehow increased by a factor of 3 due to the interaction of the X-ray burst with its surroundings. Another example for you 1820, I will be a little more quick on these ones, as Gaurav already showed these figures. And in that case, what you see is that these residuals become more and more even more systematic actually and significant. These are several epochs within a burst, and then you here in the middle panel you see how the blackbody emission is actually does not fit the observed X-ray spectra actually. And this is again the same picture, but I just want to note that FA values now can be as high as about 10. So we don't really know at the moment. There's no in the RXT era there were a few studies, but within the NICER there's no systematic search for the moment. We are just basically simply collecting more and more X-ray burst observations, let's say. But we don't really understand. We haven't understood that how the FA values are actually changing. Do they really depend on the accretion rate, on the peak flux of the burst, on some other properties of the sources? Is it related to the basically accreted material and so on? This is just another example of 4U1820 of another different burst where you see the FA value increases by a factor of about 20, which means that the persistent emission of coming from the accretions, this should be much larger, by a factor of 20 times larger than what it was before the burst. And this is just another example of X-ray spectra to show you the residues and the broadening of the spectrum compared to a pure blackbody function actually. So one thing that I would like to show is some preliminary results from another source, X1, in which we have about 22 X-ray bursts observed so far since 2017 with NICER. As you can see, we have another secondary peak that needs to be studied, let's say, in detail. But again, an interesting one, seems more or less what we observed in the first burst from 1608. This is burst 20, so it's actually this past summer, summer of 2020, outburst, it was observed. And another, and the first photocircuitous expansion burst from this source has been observed with the NICER. So these are just a few examples of time evolution of spectral parameters throughout the bursts. Again, as you can see, there are a few things that I would like to note. This FA value here is what I've been talking about, like people already reported before. So in these plots, you see in the red, with the red crosses, a pure blackbody function fits to the bursts, which shows systematically high chi-square values, as you can see. And then in the black crosses, you see the model where we introduce this FA factor. So we allow the persistent emission to increase to some degree by some factor. And often, of course, to the ends of the bursts, it's not really needed at all. So it's actually a tiny value. But it allows us to actually minimize the chi-square values at the peaks of at around the peaks of the burst. But what is more important is that, I guess maybe in this slide I can show, it actually changes the way we actually understand the bursts as well. For example, this burst 18 is a photocircuitous expansion burst, at least that's what we thought about it, let's say, in the beginning. But you see the significant normalization evolution if you do fit this X-ray spectra, NICER spectra, via simple blackbody functions. You see that the photocircuitous expanded, the temperature cooled down to some value about like 1 keV and then increased back and so on. This full story that I've been talking about based on the data from RXT. But when you look at the chi-square values when it comes to the NICER data in the soft X-ray band, you see that they're practically the worst chi-square values that you can see, let's say, in the world of X-ray spectroscopy. So you really need to improve your model somehow. And the simplest way to do that is actually, as I've been talking about, this introducing the FA model, because it introduces one free parameter, which would increase the basically emission coming from the persistent spectra. And that already introduces a lot of change in the inferred physical parameters. First of all, as you can see in the black, the peak flux increases significantly, the temperature increases that you measure, the temperature values that you measure, and the normalization values that you measure significantly decrease. And this is just another example of burst, the burst 20, the one that showed, that seemed to show actually this secondary peak, in which case you actually see again the contribution from the FA value. So we have been doing some basically exercises, let's say. These are all preliminary results, by the way, I must say. Hopefully it will be finished soon. And this is just simple chi-square distribution from the time result X-ray spectroscopy of all the bursts that we have observed from NICER. On the right-hand side, you basically see practically the same plot for all the bursts that we have observed from the RxTE back in till like all the data till 2008, and you can see the change in the x-axis. Back in the RxTE data, let's say we had the chi-squares of about like 1, 2, and so on, whereas in the case of the same model, which will be the blue histogram that's shown here, in the NICER data, we even see chi-square values of 8 and so on. So practically completely not valid fits at all. When you introduce the FA parameter that I mentioned, basically allow the persistent emission of the accretion disk to increase in time, then you significantly change the chi-square value actually. And this is the FA distribution of all the FA values that you can infer from a given from this source. The peak in the lower end is not valid actually anymore, but you can concentrate on the fact that yes, there are some FA values which seem to be within like 1 to 2, 3, a factor of 2, 3 increase in the persistent emission. But then there are, in some rare cases, which is actually related to the photospheric radius expansion burst, I guess, the FA value can be much higher. And in each case, when you introduce this, when you allow the persistent emission to change in the accretion disk, basically, you see a significant change in the spectral parameters you infer. This is very important because this is the way we have been using, or people have been using to infer physical parameters of the neutron stars, for example, the mass and the radius and so on. And so if you assume that there is some FA value, there's some increase in the persistent emission, then for example, the temperatures, as I've already mentioned, significantly increase compared to not assuming that, not allowing for such a variation. This is practically the same thing. On the x-axis, we have the normalization and temperature values that seem to be coming from only pure black body emission. And on the y-axis, we have the same parameters when we actually allow the persistent emission of the source to actually change. And color code shows the value of the FA, which seems to be increasing again, depending on the emission. Overall, the interesting thing is that only at the very high end of the FA value, or at the very large fluxes, the total flux doesn't seem to be changed too much, at least significantly. But the parameters, the spectral parameters, do significantly change. So how do the FA value actually change, or what does it depend really on? Aquila X1's data, at least for the moment, seems to be giving us some hints on that. These are, on the y-axis, the peak values of the FA parameters that we infer for a given X-ray burst. And then on the x-axis, we have the peak of that peak flux of that particular burst. And it seems like the higher the flux you observe from an X-ray burst, the higher the FA value is. So it actually shows that the more burst emission also means that you have to increase the emission of the persistent emission, basically the emission from the accretion disk, more as well. This seems to be fitting in the scenario where actually what happens is that when the burst when the burst starts to happen, it actually irradiates the accretion disk surrounding the neutron star, which basically ionizes and then seems to be actually changing in time. But this is not. But there are cases that this is not the case. So that's an interesting question as well. 1739, XDJ 1739 is another source that we observed many bursts. Actually, about 32 of them are shown in here, and in this source, we do not seem to be in need for any kinds of contribution or change in the persistent emission. At least statistically, it was not that much necessary. One thing to note here is that we do not know whether if this is a selection effect due to the, for example, change in the hydrogen column density, because that basically absorbs the soft X-ray band in the time result spectroscopy, or the fact that some of the sources are far away, so they are actually on average much more dimmer and so on. But one interesting thing is for U1608, for example, as I've already mentioned, the burst that GÜVER showed needed an FA value as large as like a factor of 10, whereas in 2020 we observed actually in total, I guess, 3 X-ray bursts. So this is one of those examples, and actually the brightest one that we observed in this past summer, where in this case the chi-square values seem to be just perfectly fine without making any introduction of the FA value. So this is the same source, practically the same brightnesses regarding the peak fluxes, regarding the peak fluxes, the same hydrogen column density value and so on. But it seems to be there seems to be a time dependence in this whole thing. And what is interesting is that it may actually be about the photospheric radius expansion, because the larger FA values we observe actually are coming from, for example, 1820, which shows really extremely large photospheric radius expansion. And then, for example, in the X1's examples that I've shown, the largest FA values we inferred from are coming from the burst that we actually show that we see a photospheric radius expansion event. The same is true for 1608 as well. The burst that shows the secondary peak also is a candidate for a photospheric radius expansion event. Not that much significant maybe, but still needs an FA value, whereas the burst that I have been showing that we observed in 2020, for example, doesn't show any evidence for a photospheric radius expansion event at all. So it may be something related to this. One other thing that we can do, at least in cases where the deviation from a pure black body is the most significant, is that we can actually, instead of introducing this FA value, we can actually fit the burst spectra with 2 black bodies. Instead of 1 black body, we can use 2 black bodies. This is an example that has been applied by Peter Bult for SAX J1748, where we have this 1 black body function that seems to be following the expected, let's say, burst black body, and another black body that seems to be more or less constant throughout the burst, but at a much larger radii. So it seems to be coming from the disk or something. And in fact, actually, that is something that we can do for, that we try to do for 4U1820 as well, where the residues are much more evident. And these are just some preliminary X-ray spectral analysis coming from that source, and introducing a second cooler black body, for example, with a temperature of like 0.15 keV, the chi-squares can be changed significantly. So one thing we can do, and we have been doing for example, 4U1820, is that we can actually fit the theoretical atmosphere models already published, for example, Süleymanov models and so on, with these kinds of 2 black body functions, which is what is shown in here. We have the theoretical models fitted with 2 different black body functions. This is in pure, let's say, model space, and then calculate at a given luminosity level for a given physical parameters, of course, log G, hydrogen abundance, and so on. we can calculate to what degree the second black body should be contributing to the burst emission, basically the ratios and so on. And we can then compare this with what we observe using the nicer data. And this is what we have been working on. And what we see is that the amount of models, for example, atmosphere models of these burst atmosphere models, indeed do introduce some broadening in the black body function and Plancking function, as evident from in these plots, for example. But it is not that much significant as what we observe from the observation. So the observation seems to be requiring an even more significant broadening compared to what one would expect from the atmospheric emission from these sources. So let me conclude around here. I guess time is up also. Is that NICER is really a lovely instrument because it is really agile, flexible, and really does the job very well. It doesn't generate images, so it's not perfectly good for dim sources, but when your source is bright enough, let's say, brighter than some values, of course, it really becomes very fun to use the data from NICER. And it actually already started. Excuse me.
Last minute.
What?
Last minute.
Okay, perfect. It really allows us to actually pinpoint all the burst properties in a different window, and it is really good. I guess the best would be to for the NICER to be working in together with RxD, but that's not possible at the moment. But it still generates very good data, and hopefully it will allow us to understand what these residuals are in time, especially regarding whether if they're actually reflection from the disk or some sort of an atmospheric component. So thank you very much.
And thank you for this nice contribution, Tolga. And I noticed 2 questions in the chat panel, but we have no time for them. Please continue via the chat panel for question and answer session. And let me introduce the next speaker.